Hello all, I'm Professor Snehal Shinde from JSPM Narhe Technical Campus. Today we are going to study the subject computer graphics, and from this subject we are going to see some of the topics from Unit 5, Shading and Hidden Surfaces. So the points to be discussed in today's session are visible surface detection, then hidden surface elimination, then why we are going to study visible surface detection, what are the different approaches for visible surface detection, and what are the coherence properties in computer graphics. So we will see each of the points one by one. Now first, that is, what is visible surface detection? So when we view a picture containing non-transparent objects and surfaces, then we cannot see those objects from view which are behind from objects closer to eye. We must remove these hidden surfaces to get a realistic screen image. The identification and removal of these surfaces is called hidden surface problem. Now, in simple words, I will tell you what is the visible surface detection. Suppose I'm holding a duster in my hand, and behind that duster, I have taken one pen. Okay, so from that pen, you can see when you are looking from front side, you will see only 20% part of the pen, and 80% of the pen is hidden. Okay, so in this case, what we can say, whatever you can see from the front side, that part is visible only. Okay, so you are going to detect the visible surface here. So what is visible to you now? The front side of the duster, and only the 20% pen is visible to you. Okay, so this is the visible surface for you. Now, what is the hidden surface then? So that 80% pen is hidden behind the duster. Okay, so we can say that that is the hidden surface. So these two terms, that is visible surface detection and hidden surface elimination, these are one and the same or quite similar. Okay, because either you are detecting the visible surface or you are eliminating the hidden surfaces. Okay, so these are one and the same things we are doing. Either you detect the visible surfaces or you hide the hidden surfaces or eliminate the hidden surfaces. Okay, so this is called as the visible surface detection. Now, why we are studying this, or why we are detecting the visible surfaces, or we are eliminating the hidden surfaces? Okay, for this we will take one example. Now consider the following cube. Here I have drawn a cube. Okay, now suppose I want to fill its front face, which contains three parts. Okay, now here this is the front face. Now this cube has 6 surfaces, we can say 1, 2, 3, 4. That is side surfaces. Then side surfaces, there are 4 side surfaces. 5th is the top surface, and 6th is the bottom surface. Okay. Now what I'm doing, I'm going to color its front face. Okay. Now if I will color this with some color, okay, what will happen? This front face is containing 3 parts. Okay, what are those 3 parts? This square is the first part, this portion is the second part, and this portion is the third part. Now these 3 parts are portions of other surfaces. So this is the back surface, okay? And this portion is some part of this back surface. This big area is the portion of one of the side surface, and this bottom part, third part, is the portion of the bottom surface. Okay, so all these 3 surfaces will be hidden if I color this front surface. Okay, now what is happening actually here? That the computer is processing information of all these 3 portions. We know that whatever we want to display on the computer screen, all the information of that image is processed, right? So the information of this particular portion is also processed. Then again, for this part also, the computer has processed the information of this second portion also, and it has processed the information of this third portion also. Okay, so we are, and finally what we are doing when we color this part, all these three parts are going to be hidden. Okay, so we are unnecessarily wasting our time in processing the information of these three parts. Are you getting? So we don't want to waste our time in processing this part. Okay, so what we would have done, we would have processed the information only of the visible parts. Okay, whatever is going to be hidden, we are not going to process the information. Okay, so here, that's why, to eliminate or to reduce that time, okay, so processing time to render this image is increasing. Now what is rendering? Whatever we want to display on the screen, that is called as a rendering. Okay, so we are rendering whole cube here. Okay, so if we are going to hide some of the parts, some of this cube's part, we should not actually render that part. Okay, so what we will do, we will first identify the visible portions, and then we will remove the hidden surfaces from the image. Okay, so here we are reducing the time to render the image. Now, as I said that we are going to see different approaches for the visible surface detection. So there are two approaches. First is object space method, and second is the image space method. Okay. Now these two methods are doing the same task. That is, they are either detecting the visible surfaces or they are eliminating the hidden surfaces. But just the method they are using is somewhat different. That's why we are going to see these two approaches. Okay, so we will see directly the comparison between them. Okay, so first is the object space method, and second is the image space method. Now, first object space method, what it does, it deals with the physical coordinates. Okay, we know that each image has its coordinate information. Vertices has the coordinates, edges has the coordinates. Okay, so this method, while detecting the visible surfaces, it deals with the coordinates of that particular object. And in image space, what it does, it deals with the viewport or the projection port coordinates. So first its projections are taken, and then we are dealing with that projected image here. Okay, here directly we are dealing with the physical coordinates of the object, and here we are dealing with the projection coordinates. Okay, now next is what, for object space method, for visibility, it compares the objects or the parts of the objects. Okay, so it will take the polygons, it will directly check its surfaces, whether they are in front of the other object or they are behind of the other object. So again, the same thing, that we are dealing with the objects here. Okay, and in case of image space method, visibility is defined by checking point by point each pixel on the projected plane. So again, we are dealing with the projected image itself, and from that projected image, each and every pixel is considered whether it is visible or not. Okay. Now, it is basically used in line display algorithm or the vector graphics system. So as I said, we are dealing with the coordinates. It is mostly used in the vector graphics system, and it deals with the line display algorithms. And here, it is used in raster scan systems, where along with the line, surfaces are also used. Now it concentrates on the geometrical relationships among the objects. Now this is, again, we can say that the improvement of the first point itself, that it deals with the coordinates. Okay, because here they are considering the geometrical relationships among the objects, and here it concentrates, this image space method concentrates on the projected final image. Now, geometrical calculations are precise. Okay, what does it mean? It's the geometrical calculations are precise, means you get the accurate image over here, as it deals with the floating points also. Now, as we are going to use the floating points, we have to use that that which capable processors also here. Okay, So if you zoom in that particular image over here, in case of object space method, the image will not be blurred. So you get the accurate image in case of object space method. And in case of image space method, calculations are done at the pixel level. So here, if you zoom in the image, you will get somewhat blurred image. Okay. Now, next point is what? Increased processing time. As we are saying, we are getting some accurate, or the images are precise, calculations are precise, and we are getting the accurate image over here. Definitely, the processing time will increase in case of object space method, and then comparatively, here it takes a less processing time. Okay, so if you want accurate images, you go for object space method, and you want images in less time, then you can go for the image space method. Now there are various algorithms that are going to use these two methods, that is object space method and the image space method. Okay, and some algorithms use object space, some algorithms use image space, and some algorithms use both these messages combined. Okay, now we will move to the next point, that is coherence properties in computer graphics. Now, what do you mean by the coherence? Okay, coherence means, we can say in simple words, the similarities. Okay, it denotes the similarities between the items or the entities. We are going to find out what are the similarities between the entities. Now, it describes the extent to which these items or entities are locally constant. In many cases in computer graphics, we use information about the objects depicted to reduce the amount of processing needed. Okay. Now, as I said here, the previous example, that if this is the cube and we want to color this particular part, okay, and when we color this front face, we are hiding now this portion of the image. Okay, so we don't want to render it. We should not detect this, or we should not process its information. Okay, now because we are unnecessarily increasing the processing time over here. Okay, now so we are going to see some of the properties, how we are going to detect the visible portions only. Okay, with the help of this coherence properties, we are going to find out the similarities of the items. Okay, and then only we can reducing the time, processing time. Now, what are the applications of the coherence in visible surface detection methods? So it makes use of the results calculated for one part of the scene or image for other nearby parts. Okay, and it is the result of local similarity. As objects have continuous spatial extent, object properties vary smoothly within a small local region in the scene, and calculations can then be made incremental. Okay, here I'll give you the example of a scene. Okay, we have already discussed this particular scene in segments and animation. Okay, suppose I have drawn a picture where there are different entities in that picture, or we can say sub pictures are there. What are the sub pictures? Suppose first mountain is there, then one tree is there, one river is there, and one bird is there. Okay, now I want, the bird is sitting at the mountain. Okay, now I want to move that bird from mountain to the tree. Okay, so what I will do here, because all other, I will consider the entities of this scene. What are the entities? Mountain, river, tree, and the bird. Okay, when the bird is moving from mountain to the tree, my other three entities, what are those three entities? Mountain, tree, and the river are going are remaining the same as it is. Okay, in every scene they are still, they are at the same position. Who is changing position here? Only the bird is changing position. Okay, so in very first image, what I have done, I have calculated the pixel properties, or whatever the picture information I have calculated for tree also, for mountain also, and for the river also, similarly for bird also. Okay, but I know that in other pictures, these three properties of the tree mountain and river are not going to change. Okay, so I will copy paste the same properties over there. Okay, so similarity I'm detecting here. This is the coherence. I'm using the same properties of these three entities in each and every image. What I'm going to do now, I'm going to change slight difference. I'm making slight difference in the position of the bird only. Okay, so calculations can then be made incremental in case of bird only here. Okay, all other results of the same, they are of the same local similarity. Okay, so what we are doing here, we are making use of the results calculated for one part. Once I have calculated for one scene, all the picture entities, I have processed the information that I'm going to use same for other images also, but only slight difference I'm making in case of bird only. Are you getting this? Now, what are those coherence properties? Now, there are n number of properties, but we are going to discuss some of the basic properties here. Okay, what are those properties? First is the object coherence, then phase coherence, age coherence, area coherence, then implied age coherence, span coherence, depth coherence, and the frame coherence. Okay, again, these are doing, all of these are doing just, they are detecting the visible surfaces. Okay, some, again I'm saying that some methods are different, or we are considering those objects in different context here. That is just the difference. So we'll see one by one each and every coherence property. Now, first is what? It is the object coherence. Okay. Now, visibility of an object can often be decided by examining a circumscribing solid, which may be of simple form. For example, it may be a sphere or a polyhedron. Okay. Now here, what is the main concept? That here the objects are separate. That is, they are non-overlapping objects. Okay. So this coherence only compares the object dimensions. Again, I will give you the example of duster and the pen itself, right? In one hand, I'm holding the duster, and in another hand, I'm holding the pen. Okay. Now, these two objects are separate, that is, they are not overlapping each other. Okay. So, in this case, what is the coherence? It will compare single objects dimensions only, because both the parts are visible here now, as they are not at all overlapping or intersecting each other. Okay. So, it will compare only the object dimensions single. First, the duster calculation, duster object dimensions will be taken, then object dimensions of the pen will be taken, and they will be displayed on the screen. Okay, so this is called as the object coherence. The second property is what? Phase coherence. Now, what is phase here? Phase may be the surface of the polygon, it may be the line, it may be a side, or it may be a polygon. Okay, so this is the phase coherence. Now, if you are looking a duster from front side, you will see a rectangle. Okay. Now, if you are checking information, that is color, shading, visibility of any random pixel from that surface, then we have more chances of having its adjacent pixels belonging to same surface with the same pixel information. For example, now as I said you that I am holding a duster and you are looking from the front side, okay? And I'm saying that you can see only a rectangle when you are looking from the front side to the duster. Okay, so suppose that this is the rectangle that you can see. Okay, now I'm just picking up any random pixel from this duster or from this face, from this surface. Okay, this is the surface now. Okay, and I'm picking one pixel. I will now check the pixel information. What is the pixel information or the pixel property here? It may be its color, shading, its visibility, etc. Okay, so I will check that. Now there are more chances of, if I check its adjacent pixels. If this is the pixel, now I am picking up second pixel or third pixel or the fourth pixel from this surface only. The same, there are many chances or more chances that all other adjacent pixels have the same color information or the pixel information that the first pixel is having. Okay, so this is what I have written here. You are checking the information of any random pixel, then we have more chances of having its adjacent pixels belonging to the same surface with the same pixel information. All other pixels will also have the same pixel information as of first pixel. Okay, so this is the face coherence. Now, third is the edge coherence. Edge coherence means what? The visibility of an edge changes only when it crosses another edge. Okay, so if one segment of a non-intersecting edge is visible, the entire edge is also visible. Now, just imagine that this is the polygon and it's one of the edges extended here. Okay, now this edge will be visible to you up till when? Up till no other element is in front of that particular edge. Okay, now here maybe this edge may be extended up to here. Okay, but now as I have kept this particular object here, some part of that edge is hidden. Okay, so what this edge coherence is saying, that visibility of edge changes only when. So up till this particular edge was visible to us, but it changes when it crosses another edge. This has come in between. Okay, so now this edge is partially visible to us. Okay, so what we can say, that if one segment of a non-intersecting edge is visible, okay, if the edge is non-intersecting, if this object is not kept over here, what I can say, if this is a non-intersecting edge, then if I say that some part of this segment is visible, then I can say that the entire edge is also visible. Okay, so this is called as the edge coherence. Now next part is what? The area coherence. Now what do you mean by this area here? Area means it may be a window, it may be a portion. Okay, now suppose, consider that this red pen border, whatever rectangle I have drawn here, this is your screen. Okay, now if your screen is divided in say 4 to 5 areas, now what I have done here, 4 areas. So this is the first area, second area, third area, and this is the fourth one, bigger area. Okay, now this screen is divided into say 4 to 5 areas. Now there are chances that all the pixels in the same area have same properties. The same information we are repeating here, okay, but in different context. Now here we are considering this for area coherence. Okay, now what I have done, I have divided the screen into 4 areas. Now if I consider this third area, okay, 1, 2, 3 and 4, the third area I'm considering, I'm taking only 1 pixel from here. Okay, so and 1 pixel information. Now there are chances that its adjacent pixels or all the pixels in this particular area have same pixel information. Okay, so group of adjacent pixels in an image is often covered by the same visible object. Okay, so this coherence is based on the assumption that a small enough region of pixels will most likely lie within a single polygon. So what is the use of it? So this reduces the computation effort in searching for those polygons which contain a given screen area, as in some subdivision algorithms. Okay, so again the same concept we are seeing here. If one pixel has some properties, then in that area all the pixels may have the same properties. Okay, so this is called as the area coherence. Next is what? Implied edge coherence. Okay, now suppose we have a polygon, say this triangle is given here. Okay, and one scan line. Okay, we may consider one scan line or some other intersecting polygon we can see. Okay, we have, so for now we will consider this polygon and a scan line. Okay, and what I have to do, I have to find out this intersection, the coordinates for this particular intersection point. How can I find out here? We have already seen this concept in say a scanline polygon filling. Okay, we had found out the coordinates of this particular intersection point with the slope intercept form. Okay, for that what we had done, we had considered this scanline is crossing this particular edge of the triangle, so we will consider this x1 y1. points of this vertex, then other endpoint of this line, x2, y2. So we will consider these endpoints coordinates, and then we will use the slope intercept form or slope intercept equation, and then we can find out the coordinates of this. So the same is given here, that is implied edge coherence. That is, if we have a triangle and we have a scan line and we have to find out the intersection point here, then the polygon edge with the slope intercept form using endpoint coordinates of the polygon edge, we can find out the intersection point. Okay, so this is called as the implied edge coherence. So next is what? The span coherence. Now what do you mean by a span? It is a group of adjacent pixels lying on the scan line. Okay, span is what? Now suppose, consider again this triangle I have drawn here. I have drawn a scan line y. Next scan line is say y minus 1, y minus 2. I have drawn 3 scan lines here. Okay, now suppose we know that each line is made up of pixels, discrete pixels. Okay, each line is made up of discrete pixels. Now suppose I have selected first 10 to 15 pixels. So this group of 10 to 15 pixels is called as a span. Okay, I have made this span, the second span, third span, and fourth span, like this. Okay, so group of pixels, span is what? It is a group of adjacent pixels lying on the scan line. Okay, then the pixel properties of all the pixels in a particular span may be same. The same concept again we are repeating here. If the property of this particular pixel is say xyz, then there are chances that in this particular span the properties of all other pixels will be same as this first property. Getting? So this is called as the span coherence. Next property is the depth coherence. Now what do you mean by the depth? It is the distance between the pixel and the viewport of the camera. Whatever you are standing, suppose in at one position holding the camera, so the distance between this particular pixel and the camera position is called as the distance or depth. Okay, and or it is also represented by this z value. Okay, so the z value of the adjacent pixels of a surface of polygon will change slightly or smoothly. Okay, now just consider one example here. I have drawn one polygon here. Now suppose this particular pixel I have picked up, okay, and I have found out that its depth is what? It is 300. Now, what will be the depth of its adjacent pixel? It may change slightly, okay. So, it may be 295 or 298 or 301, okay. So, we can make slightly incremental change in the depth of its adjacent pixels. So, that is called as the depth coherence. And last one is what? Frame coherence. Now what do you mean by frame coherence? We have seen again in segments and animation that for each and every picture or animation, what we are doing, we are generating different frames. Okay, so in animation we generate always the frames. For example, we are generating 30 frames per second, okay, for one particular animation. Now, one image is generated with a 30 image having slight changes. Consider the same example that I have already given you. The scene, the bird is moving from mountain to the tree. So, we are making slight changes in the position of the bird only. All other entities are remaining as it is. Okay, so the properties of each frame may differ slightly. Okay, so we can reduce the calculation part and in turn time by copying the previous frame properties. So we will copy the frame properties for mountain, tree, and river as it is, and we are making slight changes in the properties of the bird only. So this is called as the frame coherence. Okay, so in this way we have seen what is visible surface detection, what is hidden surface elimination, then why we are studying the visible surface detection, what are the approaches, The two approaches we have seen here, that is the object space and the image space method. And then we have seen 8 basic coherence properties in the computer graphics. Thank you.